So the broken road of innovation, right? So as we all know, innovation is hardly a straight line or a smooth curve. And many times the outcomes and the true breakthroughs can't even be predicted, right? So what you have though is a talent for maybe connecting some dots that other people, just couldn't connect. The dots were all there, but it took an insight. And since we're talking about artificial intelligence applied to biotechnology and then ultimately drug discovery, what we're really trying to understand is, well, look at some patterns. So the history is full of examples of this. Louis Pasteur, when his colleagues said he had a failed experiment, he looked and wondered, well, why did those chickens survive when they should have died? Well, suddenly we have a vaccine as a result, right? And even Arthur Fleming thought his experiment had failed when bread mold got into his petri dishes, but he took the time to wonder, well, why was it killing some of the bacteria that was there? And thus we have penicillin, right? So now we have a very interesting intersection where we have computer science and artificial intelligence and language that's now being applied to research and understanding. And now we have tools that can scour deep research, connect dots automatically in a sense via software, and give researchers new tools and really a dynamic way to make potentially some significant breakthroughs. And so when I say text to breakthrough, the specific example lately, right, is we have this from OpenAI, we have this ability, right, to text and we get an image, right? So now people are wondering, well, is this going to now obviate the need for artists? And of course, I will say absolutely not. Creativity is creativity, and a text message that generates an AI image is not really that creative. But the real issue here is you have a plaything that sort of keeps us amused, and I call it the untalented and unimaginative. Because if you're really creative, you'll sort of go ahead and do your own thing. But the interesting thing, and the point I want to make, is to be very talented and very imaginative, this is a very powerful tool to do research and to impact scientific discovery and really bring the whole field forward, right? So we have, I call it a protein in a picture, right? So we say, well, you probably understand this from basic biology, but you have, 20 amino acids in the body. They combine in some certain ways to create proteins. Those proteins combine, and they call it folding, protein folding, to create a protein complex. And that protein complex basically tells your body to do something, right? So your body doesn't do anything unless a protein or a complex of proteins told it to do so. But creating those images and creating those proteins that can send very helpful signals to address unmet medical needs has been an almost impenetrable problem because of the complexity involved. Well, now we have a software tool that can do that, right? So biology's greatest challenge, like how do we really tell the body to do the right thing or maybe not do the wrong thing, whatever it is, can it really be reduced to a text message, right? So, this AI tool can really enable, if you will, connecting some of those dots or connecting that broken road that I refer to. All right, so one of the things to understand as we back up is when it comes to designing anything, evolution wins. Evolution's had billions of years to figure stuff out. And in another presentation, I talked about the CRISPR technology, which is essentially bacteria's way of fighting viruses. Bacteria spent 3 billion years figuring that out. It does it pretty well. But now that's a tool that we can use for potentially, medical therapies. And that's, a fantastic breakthrough. But using evolution to our best ability is maybe the real goal of drug discovery and life sciences in general, right? So we have, building blocks of living systems, which are these proteins and protein complexes. And so what we can do with the software tools is essentially accelerate evolution, right? So we can say, well, what happens if this occurs over the equivalent of millions, maybe even billions of years? And we now have computing capacity and software tools that can enable that. So we can get alongside evolution. And one of the big issues with side effects to any drug, and people in the field understand this, the basic reason drugs have side effects, sometimes very bad side effects, is you're actually getting in the way of evolution. A cell functions in a certain way and you're telling the cell, well, stop doing that because that leads to a disease or an undesirable outcome. Well, that function actually has something embedded in it for nature as well. And so you're stopping that. Even when you saw the drug Vioxx, which was inhibiting pain quite effectively, but was also inhibiting the signal to the body that, we're having a cardiac arrest. We have to do something. So that's why you had, these cardiovascular issues with Vioxx. And then, of course, the other example is sickle cell anemia, which unfortunately is, such a paralyzing disease. But the genetic capability that induces the disease also prevents malaria quite effectively, right? So there is a function. So just shutting down a function, which is what most of life science and most of biotechnology unfortunately really does, it gets in the way of evolution. So you have side effects, and sometimes you just lack efficacy as a result of that. So when we talk about biology versus computation, right? So evolution, biology, it's, your body is an amazing software system. And understanding how that software system works and using computation to understand and then help treat disease is really the goal here, right? Now, unfortunately, we just have not been getting this right. Now, over the years, many people have said, well, if we just, go through a whole series of computations, we'll find compounds that will work. Well, that just really didn't lead anywhere. We'll just test everything, and then ultimately we'll figure out on a test tube, on a chip even, something that works. Well, it doesn't really work in the body. The body is far too complex. One of the things that is the great flaw of computer science is, well, we sort of have if this, then that, this or that, this and that, right? Welcome to computer science. That's not how your body works. Your body is a very complex interacting system, and simply affecting one element doesn't necessarily give only the outcome you're looking for. It gives many other outcomes, and it's really the law of unintended consequences. And I say, promising is not reality. We find a lot of promising things. There's a joke that says, well, we can cure cancer in mice, we just can't do it in humans. Well, that's the problem. There's something that's promising, there's something that's plausible, and there's something that is probable, right? We haven't gotten to the probable stage yet. We're sort of going from promising to plausible. We're seeing what could be, great advancement, but we are not in the probable stage yet. And so when you have, the tool that understands, look, proteins have a certain shape, right? And that shape defines its function. So again, amino acids combine, they create proteins. Those proteins combine, they create a certain shape. That shape has a certain signal that your body understands and performs whatever function is designed there. So then turning around and flipping that, saying, well, let's figure out what the shape ought to be. Let's see the function that's going on. Let's figure out what the shape ought to be in order to do that function. And now let's create something, right? That's what we're really seeing with this kind of, I'll call it text to image tools that we're using in life sciences. Well, that doesn't mean that's going to happen, right? Because, what we have seen, and, more and more study when you see these certain shapes, and I call it, strange on a screen, obvious in nature, right? Once again, a computer doesn't quite understand why that shape should be that way, but nature does for some reason, and it's had a long time to figure that out via evolution. But now we turn around and try to make those strange shapes that would be unimaginable, and we're seeing some of that progress with DeepMind and their AI programs that have understood protein folding and have led to some very unique and innovative drug designs. So we're seeing more and more of that, but I want to caution this, that we're doing the problem, or we're solving the problem in reverse. We're saying we want that function, let's figure out a shape that does it, right? That may or may not work, because, if you get the design right, that doesn't mean you get the function right. In other words, you sort of, a great example is, well, you can design anything you want. If you don't build it, it's meaningless, right? The same thing here. It's like, we know the function we want. We're trying to reverse engineer essentially via artificial intelligence to get the design that may work, and it certainly is a broken road to get there. But that's what I really mean, like the myth of the straight line, right? We're not able to just say, okay, let's go from here to there, right? So, one of the things that we can step back and be comfortable with is, we have this pervasive tool that's developing, which is artificial intelligence. We have an ability now to use a very simple query in the case of, the current OpenAI DALL-E 2, GP3, wherever they are now. We can use that tool to make a query and to get, an answer. But now we're looking for more depth and more robust designs that we can then test, right? So all of this takes a lot of time. This is the epitome of sort of, well, we don't really know where this is going, let's try, and suddenly you have an astonishing result, right? So you have, the law of unintended consequences that can be very, very positive, or very negative, right? One of the discussions I had earlier where we talked about, well, look at the people designing, the Manhattan Project, right? So at first, many of those physicists believed that nuclear energy could solve energy problems for humankind. We could have clean, limitless energy. That was really the driving force behind a lot of the initial nuclear research. Well, now suddenly we said, well, we can make a bomb, and we've got a war. Let's end that. Let's end that war. That was a good thing, right? Let's go after a tool that can end, all this bloodshed, right? Well, nobody thought about the consequences, right? So, very famously, Robert Oppenheimer sees the nuclear, or sees the mushroom cloud from his nuclear explosion and goes, what have I done? Right? So now we've unleashed something potentially horrible with the intention of doing something, fundamentally good, right? I mean, even though you're designing a weapon, you're hoping to end bloodshed, right? So, we really have to understand those consequences, but you can have astonishing positive results. You can have astonishing negative results. Usually it's a mix, and you have to understand this. And one of the reasons why drugs have side effects is because we're interfering in a very well-designed, evolved software system, and now we're trying to tweak it to do something better. Well, that's challenging, but I still think that we can get there because now we have an ability beyond human comprehension to design and develop breakthroughs. And that is really kind of the point to this new advancement and why this can be very encouraging. Right? So we say in summary, we have an easy interface, a text tool that can then guide research, great depth of research and understanding, connecting dots that we really wouldn't be able to connect. That's really the breakthrough, the ability to look at the whole landscape of research and understanding and start putting things together and seeing how things can potentially work, right? And I say evolution always wins. Let's get on evolution's side. What problems has evolution solved? Let's kind of ride those coattails, right? And that's when you look at some of the anti-inflammatory medications that can be very effective because evolution has figured out how to deal with inflammation, right? We looked at, again, CRISPR, I mentioned that, but some of these breakthroughs are doing nothing more than guiding the results of evolution to our benefit. And so, again, we are not a simple equation. Computation, that's the fundamental flaw here. Computation is not biology. Biology is a very involved, integrated system. Things can work in a test tube, they can work on a software screen, they can work in initial testing, but when you finally see the results in human beings, you get unexpected consequences. Some good, mostly bad. We have to understand that that's the broken road that we're on, right? So to look for real innovation, the point here is work as hard as we can, try what we can. We're going to have a lot of failures, but as I've said in other presentations, failures are not failure, right? Failures teach you something, they guide you, they get you along. One of the reasons that Arthur Fleming stuck with his discovery of penicillin was that he failed in trying to come up with a different kind of antibiotic using lysosome, which is an enzyme in human saliva. He failed at that, but that failure led him to say, well, there's got to be something that works better. Again, he was thinking evolution has figured this out. Evolution knows how to fight bacteria. What am I missing? And suddenly, a piece of bread mold lands on a petri dish, right? So that's the epitome of the broken road. And I think we're on that pathway now with very robust, universally available tools that I think can lead to extraordinary breakthroughs. And I'm very, very encouraged about the advancements in life sciences to come. And this, text to image tool is merely the beginning.